Good day everyone, this is Group 9. I am Jomarr Paroan and together with Ianna Paguio, we are reporting about Andresito Acuña's Philosophical Analysis Unit 3 entitled Analysis of Deductive Argument from Modules 2 to 7. Let us begin with tackling about Unit 3 Module 2 entitled Representing Compound Statements. So let us begin by differentiating between a sentence and statements first. So a sentence is a series of words put together to form a complete idea. A sentence is typically either presented in the form of a statement or providing information or a question or requesting information. And while a statement is usually a declaration of fact or an expression of opinion, it can be true or false. So example of a statement is the sky is blue, he was late for school, and the flower is beautiful. Simple statements are statements that usually consist of one subject and one predicate, meaning that they are simply just one sentence and nothing more. So here are the examples of simple statements. London is the capital of England. London is the subject while the capital of England is the predicate. John went home. John as the subject and went home as the predicate. And the train was late. Train as the subject and was late is the predicate. So, compound statements. A compound statement is a statement that results from the application of one or more logical connectives to a collection of simple statements. It includes series of simple statements linked together by connective devices. So, here are some examples of compound statements. You will notice that there are multiple subjects and predicates in a single compound statement. The sky is blue and the grass is green. And they spoke to him in French, but he responded in English. The first sentence has two simple statements connected by the connective device end, and the second sentence also has two simple statements connected by the connective device but. Representing simple statements. So in representing simple statements, you only need to remember one thing. You only need to use a single capital letter to represent the content of the statement. So for example, we have the example here, simple statement, the house is yellow. You can represent this by using the single capital letter H that stands for house, and the H will stand for the entire content of the simple statement, the house is yellow. You could represent this statement by using the letter H or Y or any letter in the alphabet. It boils down to your own preference. You can also use A or B or the famous letters in logic and reasoning P and Q. As long as it is a capital letter in the English alphabet, any letter will do. How about we represent compound statements? It's just the same. You need to apply the rules of representing simple statements, meaning you represent them by using capital letters, but we also need to take note of the usage of logical constants or the connective or quantifiers in order to connect the simple statements together to form linking ideas. So what are these logical constants? These are connective words or quantifiers that we use to link simple statements in order to form compound statements. There are four types of logical constants. The first type of a logical constant is called a conjunction. It is represented by using the symbol bullet, and it represents the word or the connecting word and. So here in this example, Plato is a philosopher and Aristotle is a philosopher. The two simple statements are connected by the word and we represent these two simple statements by using the respective capital letters P for Plato and A for Aristotle, and we use the symbol bullet instead of the word and to connect them. The next type is called alternation. It is represented by using the symbol letter V, and it represents the words either or. So for example, either Plato is a philosopher or Aristotle is a philosopher. Just like the conjunction, we use P and A to represent the simple statements, and we use the symbol letter V in order to represent the connecting word or. So the third type of logical constants is called conditional. It uses the symbol an arrow that points to the right, and it represents if-then statements. For example, suppose you have two simple statements P and Q. You use P and then an arrow and then Q to represent if P then Q. So the next type is called a biconditional. It uses the symbol that or called triple bar, and it represents if and only if statements. So For example, suppose you have two simple statements P and Q. Just like conditional, you use P triple bar Q to represent P if and only if Q. The next is called negation. It uses the symbol tilde and it represents not or negation. For example, suppose you have a simple statement P. You can use the symbol tilde in front of P to represent not P. For compound statements, however, there are some specifications. If you want to negate only one element of a compound statement, you put the symbol tilde in front of that specific simple statement. For example, P, if P, then Q. If you want to say, if not P, then Q, then you use the tilde, P, then an arrow, and then Q. If you are negating the whole compound statement, consider the use of brackets or parentheses to mark the scope or domain of the negation. So this tilde, then parentheses, P, arrow, Q, then parentheses can also be read as it is not the case that if P, then Q. That ends Module 2, and now let's go to Unit 3, Module 3, titled Truth Values of Compound Statements. Let's talk first about principles in the analysis of the truth values of statements. There are three principles. Number one is principle of identity. It says here that statement P implies itself, and it is represented by P, then an arrow, and then P. So this statement is a tautology. What is a tautology? It is a formula or assertion that is true in every possible interpretation. And for example here, you have the statement, puppies are young dogs, represented by the capital letter P, and supposing that young dogs are indeed called puppies, so if P is true, then P is true. If puppies are called young dogs, then puppies are called young dogs because it is represented by P and arrow and then P. Reversely, if you say that young dogs are not called puppies, P will be false. That statement will then be if P is false, then P is false. So you use the symbol tilde to incorporate negation, so tilde P, then an arrow, then tilde and P. These statements are called a tautology. And when a statement is always true in its virtue or of its logical form, it is called a tautology. And we have to remember that truth values are attained indefinitely over time. They are either more or less stable. If the truth values are not stable, then the other principles will not work. So the second principle is called the excluded middle. The principle of excluded middle guarantees that the truth value of any statement like P is either true or false only. This means that the premise and conclusion of a deductive argument can only be either true or false. It cannot admit to probability values. The principle is represented by using the P and then letter V and then tilde and then P. So for example, we have here either puppies are young dogs or they are not. You do not have a third truth value. Supposing you know that P is true, then without further investigation, you also know that the negation tilde P is also false, following the principle of excluded middle. Why? Because you know that the truth of P is stable over time following the principle of identity, and you know that P can either be true or false only. Logicians have a technical name for this relationship. It is called truth-functional relations. This means that P and negation P are truth-functionality related. Now, if we consider the reverse, if the affirmative P is false, then it is the negative or the negation P that is true. When you see the negation sign before a statement, it does not necessarily mean that the statement is false. A negated statement can be true or it can also be false. So in short, P negation P is always true because in all possible substitution of its truth values, the statement is true. This means that P or negation P is also a tautology. P or negation P is a tautology because even if one of them is false, it is an or statement or an alternation, meaning you only need one statement in order for the whole argument to be true. That's why it's called a tautology. The last principle among the three principles is called the principle of non-contradiction. This principle will prevent you from assigning two truth values to a statement at the same time and in the same respect. This means that P cannot be both true and false at the same time and in the same respect. Although statement P can be true at one instance and false at another, they cannot be true and false at the same time. For instance, we all know puppies cannot be both young dogs and not young dogs at the same time and in the same respect. That would be a contradictory statement. Furthermore, this principle of non-contradiction is represented by negation parenthesis P and negation P parenthesis. It reads as, it is not the case that P and not P. This principle also features conjunction of the form P and negation P, and since it is a conjunction with one false statement, it is always false because a conjunction is true only when both conjuncts are true according to the truth table of a conjunction, which we will talk about later. P and negation P therefore is self-contradictory. The denial of a self-contradictory statement of the form negation parenthesis P and negation P parenthesis is always true, hence it is a tautology. Let's now go to the truth tables of each logical constants. The first one is the truth table of a conjunction. Here, you only need to remember one rule. In order for the argument to be true, both premises need to be true as well. The other possible combinations of premises are regarded as false. So in all other combination of the truth value, the conjunction is always false. This means that we are only allowed to conjoin two or a set of statements provided that the statements are true as well. This is the only requirement for a truth table of a conjunction to be true. It is important to note that the premises of a deductive argument, however numerous, are connected by a conjunction. This means that if one of the premises turn out to be false, the whole premise set is also false. The next is the truth table for alternation. So in this case, at least one premise needs to be true in order for the whole premise to be set to be true. The only instance that an alternation statement is false is when both statements are false. All other combinations of truth values, the alternation is true. This means that the minimum requirement in formulating a true alternation is at least one of the alternants must be true, and it does not matter if the other is false. The next truth table is the conditional. So the conditional is false only if the antecedent P is true and the consequent Q is false. All possible combinations of truth values of the antecedent and the consequent, the conditional is true. It does not matter if one or both the antecedent and consequent are false, because you only need to follow the requirement of the conditional. Logical form of deductive argument. Logicians believe that the logical form of all deductive arguments is logically isomorphic with that of the conditional statement, meaning that the truth tables of conditional statements and table of validity are similar to each other. Now, let's compare the truth table of the conditional with the table of validity for judging whether an argument is valid or not. Notice that an argument is invalid only when the premise set is true and the conclusion is false. This corresponds to the only case in which a conditional statement is false, when the antecedent is true and the consequent is false. This means that the table of validity is logically isomorphic with the truth table of a conditional statement. This further means that the premise set of a deductive argument is joined to its conclusion by the conditional connective, and remember that often cited definition of a valid argument: if the premises are true, the conclusion cannot be false. In fact, you can even have an example of a valid argument where the premise and conclusion are false, but such an argument, of course, while valid, does not have an empirical or evaluative content. Thus, the concept of valid argument form refers to the truth table of an argument where there is no case in which the premise set is true and the conclusion is false. Next is the truth table for biconditional. A biconditional is true only under two conditions: when both elements P and Q are true, or when both P and Q are false. In all other combinations, the biconditional is false. A biconditional is asserting a necessary condition that P is true if Q is true, and a sufficient condition that P is true only if Q is true. Thus, Q is both the necessary and sufficient condition for the truth of P, such that if Q is true, you know that P is also true, or if Q is false, then you know that P cannot be true or is false. The last is the truth table for negation. When negating a statement, you only need to get its reverse idea, meaning that if P is true, when you negate it, it becomes P is false. This is applicable for all elements of a representation of logical arguments. There is also a case where you can double negate as well. If you put two tildes in front of P, then the idea will become true at first, the negated once will make the statement false, then if negated twice, the statement will become true, and so on. So for example, if you negate 5 times, then the resulting statement will be true again. Also, parentheses signifies scope in negations. If you put tilde in front of a parenthesis, then it means that the whole premise set is negated. Consequently, if you put a negation sign only in front of a specific element, then that element will be the only one negated and not the whole premise set. Now let's move on to Unit 3, Module 4, Representing Arguments. Let us consider this argument. Premise 1 is a compound statement, while premise 2 and conclusion 3 are both simple statements. We can represent premise 1 by using the capital letters R for represent and A for arguments. Then we represent the conclusion indicator by using the logical convention of 3 dots, or also called the therefore sign. Our next step is to represent the argument by determining the logical structure. We put away the content of the statements and only use the representations of each statement, which are the capital letters, and the logical constant sign for conditional, which is the arrow sign. We also use the therefore sign to represent the conclusion. Let's now go to the first type of argument form, which is the valid argument form, or called modus ponens. It is the method of affirming because you affirm the antecedent. It is in the structure of 1 if A then B, 2 A, 3 therefore B. So for example, if it is raining, then the streets are wet. It is raining, therefore the streets are wet. This is a valid argument form because we can always tell when it rains, it is automatically the case that the streets are wet. We can also use the representations of this argument to put away the content. We use the symbol for if-then statements, which is the arrow sign, the capital letters as usual, and the therefore sign for the conclusion. Next is the invalid argument form, which is called affirming the consequent, and it is called affirming the consequent because contrast to modus ponens, where you affirm the antecedent, in this case you affirm the consequent. It is in the structure of if A then B, B therefore A. So for instance, if it is raining, then the streets are wet. The streets are wet, therefore it is raining. It is invalid because it is not always the case that if the streets are wet, it is because of the rain. There are some instances that the streets are wet because someone is intentionally wetting the streets for some reason, or any situation that can wet the streets other than the rain. You can also represent this argument like how we did in modus ponens. Another argument with a different logical structure is addition. It is a valid argument form, and it goes by the structure of premise 1, A, premise 2, B, conclusion 3, A and B. Let's consider this example. Some arguments are valid, some arguments are invalid. Therefore, some arguments are valid and some arguments are invalid. We represent V for valid and I for invalid. The argument structure of the representation of the argument will look like premise 1, V, premise 2, I, and conclusion 3 is therefore V and I. The logical structure of various arguments may differ, but if they are valid, they share one common characteristic in their truth tables. There is no case in which the premise set is true and the conclusion is false. So, if an argument form has a true premise set and a false conclusion, it is invalid. This is why we need to represent the argument first, and once the logical structure is revealed, the content is disregarded, we can now focus on the logical form and see if the argument is invalid or valid using the truth tables that we have just discussed. If we have a vertical way of representing arguments, there is also another option, which is the horizontal representation. In this case, the representations of the compound statements stay the same. Capital letters are still used to represent individual simple statements. The premise 1 and 2 are joined by the conjunction symbol or the bullet. The main highlight of the horizontal representation is the usage of the arrow symbol to represent the 3 dots or therefore sign, which implies that the logical form of all deductive arguments follow the logical form of a conditional statement. So now, we can be able to determine if the argument is valid or not using the conditional truth table.
Unit 3, Module 5, Basic Deductive Argument Forms. In Module 4, you learn how to separate the logical structure of an argument and its content using a basic representation approach. You understood how to convey an argument in a vertical or horizontal format. You learned that an argument is valid if there is no instance in the truth table where the premise set is true but the conclusion is false. You may also be aware that the truth table of an argument is referred to as its argument form or logical form. In this module, you are now ready and capable of distinguishing valid and invalid argument structures just by looking at them or mere inspection. Conjunction. Suppose you already know that two statements are true. These statements can be anything, even unrelated. The only criteria is they are both true. The referent of all the statements is true, and the referent of all false statements is false, according to logician Frege, or Friedrich Ludwig Gottlob Frege, a German logician, mathematician, and philosopher who helped found both modern mathematical logic and the beginnings of the analytic philosophy movement. In the following, we shall be discussing only of truth and falsehood of argument, not their meanings and empirical content. Consider the following pair of two true statements. Amphibians are animals, and birds have feathers. Let us represent the two statements as A and B. Because conjoining two true propositions preserve the truth value of the conjunction, you can conjoin A and B. A conjunction is the technical term of a valid argument. The following diagram depicts the argument structure. Premise 1. Amphibians are animals. Premise 2. Birds have feathers. Conclusion. Amphibians are animals and birds have feathers. Simplification. If conjoining two true statements retain the truth value of the conjunction, then separating their conjuncts thus as well. Thus, premise 1. Amphibians are animals and birds have feathers. Conclusion. Therefore, amphibians are animals. Or in another version, premise 1. Amphibians are animals and birds have feathers. Conclusion. Therefore, birds have feathers. As a result, you can extract any of the conjuncts A or B from a conjunction A and B. Consequently, every argument structure, such as the given example, is valid. The term simplification refers to a valid argument structure. Alternation. Suppose you know that two statements are true, namely, whales are mammals and snakes are reptiles. Then, from the two true statements, you can create an alternation. Either whales are mammals or snakes are reptiles. The argument structure of an alternation is depicted in the following. Premise 1. Whales are mammals. Premise 2. Snakes are reptiles. Conclusion. Therefore, either whales are mammals or snakes are reptiles. Remember that you have the right to make an alternation if you know that the two statements W and S are true. Similarly, you have the right to make a conjunction if you know that the two statements are true. You know that you can validly infer any of the conjuncts from a conjunction. Can you derive any of the alternants from an alternation? Unfortunately, you cannot. Subtracting an alternative is the term for the invalid argument structure. You cannot deduce any of the alternants from an alternation since an alternation is true even if only one of the alternants is true. You may infer the false alternative and you will have a case where the premise is true but the conclusion is false. The following is an example of an invalid argument structure. Premise 1. Either R or L. Conclusion. Therefore, R. Premise 1. Either R or L. Conclusion. Therefore, L. Adding an alternative. Suppose you are aware that the statement FPJ is running for president is true. Furthermore, you are aware that the statement Danding is running for president is false. Is it still possible for you to construct a valid argument like the following? Premise 1. FPJ is running for president. Conclusion. Therefore, Either FPJ is running for president or Danding is not running for president. You certainly can. Remember that if only one of the alternants is true, the alternation is true. Only if both alternants are false, it is false. Adding an alternative is the term for this valid argument. Adding a conjunct. Suppose you are aware that the statement is true. Is it possible to add a conjunction? You cannot, unfortunately, because the statement you like to add might be false. If R is true, then premise 1, R. Conclusion, therefore, R and L. It's an invalid argument. It is known as adding a conjunct. Remember that you can make a conjunction if you are certain that both statements are true. A conjunction cannot be formed by adding a statement L with an unknown truth value. Disjunctive syllogism. Detaching an alternative is valid only if you know the alternation is true, not if both alternants are true. One or the other, however, is false. This is known as a disjunctive syllogism. Premise 1, either R or L. Premise 2, not R. Conclusion, therefore L. Or, to use another variation of the same argument, premise 1, either R or L. Premise 2, not L. Conclusion, therefore R. Denying an alternative. Denying an alternative is an invalid argument frequently confused with disjunctive syllogism. It is invalid because even if you know that FPJ is running for president, you cannot deduce that Danding is running for president is false because both statements can be true. Premise 1, either R or L. Premise 2, R. Conclusion, therefore not L. Another variation of the same invalid argument is that if you know that Danding is running for president is true, you cannot infer that FPJ is running for president is false. Premise 1, either R or L. Premise 2, L. Conclusion, therefore not R. Please keep in mind that the argument denying an alternative is easily confused with a valid disjunctive syllogism argument. Unit 3, Module 6, Complex Argument Forms. This module will teach you how to distinguish between the more difficult arguments involving conditionals. When reading logic text, you are likely to come across arguments like this. This will be the conclusion of your deductive argument study. Modus ponens and affirming the consequent. Let us look at the more complicated argument incorporating conditionals. These arguments are more difficult than the conjunction and alternation argument. Acuna is sure that you are already familiar with the invalid argument called fallacy of affirming the consequent and the argument known as modus ponens. Let us have a look at them. The argument structure of modus ponens is seen in the following. Premise 1, if R, then L. Premise 2, R. Conclusion, therefore L. Premise 2 affirms the antecedent, as can be shown from the argument structure of modus ponens. You are aware, however, that the reverse, which is affirming the result, is an invalid argument. To give an example, Premise 1, if R, then L. Premise 2, L. Conclusion, therefore R. Modus tollens and denying the antecedent. Modus tollens is the counterpart of the valid form of modus ponens. The following is a diagram of the argument structure. Premise 1, if R, then L. Premise 2, not L. Conclusion, therefore not R. The valid form, according to formal logicians, is when you deny the consequent and have the valid argument of modus tollens. You can also affirm the antecedent, which results in a valid argument of modus ponens. If you do the opposite, affirm the consequent or deny the antecedent, You have created an invalid argument. As a result, if you deny the antecedent, premise 1, if R, then L. Premise 2, not R. Conclusion, therefore, not L. This argument is invalid. It is referred to as denying the antecedent. It is often mistaken for modus tollens. Remember that if you affirm the consequent but deny the antecedent, your argument will be invalid. Detaching the consequent. When conditionals are included, there is additional invalid argument to be aware of, namely detachment of the consequent. Premise 1, if R, then L. Conclusion, therefore L. You cannot infer the consequent since the consequent and the antecedent of a conjunction can both be false while the conjunction remains true. Hypothetical syllogism. Consider the hypothetical syllogism, which is a more sophisticated valid argument. The following is a diagram of the argument structure. Premise 1, if R, then L. Premise 2, if L, then C. Conclusion, therefore, if R, then C. Fallacy of misplaced middle. The fallacy of a misplaced middle is a fallacy that is frequently mistaken with hypothetical syllogism. The following is the argument structure. Premise 1, if R, then L. Premise 2, if C, then L. Conclusion, therefore, if R, then C. Constructive dilemma. Constructive dilemma is another example of a sophisticated valid argument type. The following diagram depicts the logical structure. Premise 1, either R or L. Premise 2, if R, then D. Premise 3, if L, then C. Conclusion, therefore, either D or C. Again, Acuna knows that you intuitively understand that this argument is valid since it affirms the antecedent R and L of both conditionals, allowing you to validly infer the consequent either V or C in the conclusion. A constructive dilemma is a logical union of two modus ponens. Destructive dilemma. The destructive dilemma is another valid argument type. The following is the argument structure. Premise 1, either not D or not C. Premise 2, if R, then D. Premise 3, if L, then C. Conclusion, therefore, either not R or not L. Acuna also knows that you believe the argument is valid because it denies the consequent not D and not C of both conditionals, allowing you to validly infer the denial of the antecedent in the conclusion. The argument structure of destructive dilemma is a mix of two modus tollens. Pseudo-dilemma 1. There are two types of fallacious forms that appear to be valid at first glance but are not. They are referred to as pseudo-dilemmas. The antecedent is denied in pseudo-dilemma 1, whereas the consequent is affirmed in pseudo-dilemma 2. Let us start with pseudo-problem 1, which has the following argument structure. Premise 1, if R, then D. Premise 2, if L, then C. Premise 3, either not R or not L. Conclusion, therefore, either not D or not C. Notice that the antecedent of premises 1 and 2 is denied by this fallacy. Thus, it is unable to conclude the denial of both the consequents. The argument may end by denying the antecedent if the consequent was denied. You know that this valid form is known as destructive dilemma, and pseudo-dilemma is a term which is frequently confused with it. Pseudo-dilemma 2. Pseudo-dilemma 2 is another invalid argument that is often confused with the valid one. Premise 1, either D or C. Premise 2, if R, then D. Premise 3, if L, then C. Conclusion, therefore, either R or L. This invalid argument has the exact opposite effect. It cannot affirm the antecedent because it affirms the consequent of premise 2 and 3. On the other hand, it could have concluded by affirming the consequent if it had affirmed the antecedent. Constructive dilemma is the name of this valid argument, and pseudo-dilemma 2 is often confused with it. Remember the rule. If you affirm the antecedent or deny the consequent of a conditional, you will always have a valid argument. Unit 3, Module 7, Truth Table Method. This module will show you how to use a sophisticated strategy for assessing if an argument form is valid or invalid. That technique is called the Truth Table Method. It is a quick and efficient way to figure out whether or not an argument is valid. To apply the Truth Table Method effectively, you must first go through a series of steps. First, you should represent the argument horizontally, like follows. If R, then L, and R, then L. Next, you have to count how many simple statements in the argument. R and L are the two you have. Now you must create a table with all of the possible truth values, R and L substitution instances. The following table will show you how. If your argument has 3 statements, such as R, L, and Q, you will have the following table with 8 rows. These are all possible truth value substitution instances for a 3-statement argument structure. With 4, 5, or 6 statements, you might do the same table of substitution instances in an argument form. Acuna is sure that you can see how complicated the table will be. With 4 statements, there will be 16 rows. With 5, there will be 32 rows. With 6, there will be 64 rows. And with 8, there will be 256 rows. Finally, you must assign the truth value to the statements in the argument structure when you have completed your table of substitution instance. Take note of how the table made it easier to apply truth values to the structure. To give an example, please observe that no horizontal exists in which the premise is true but the conclusion is false. Consequently, the argument form is valid in all possible substitution instances of the truth value of the argument statements. As a result, it is a tautology. Although we refer to a specific argument as valid or invalid based on its particular truth values, valid argument forms technically correspond to the truth table, just like the given example. Let us look at an example of an invalid form of affirming the consequent. You are probably aware that this argument is commonly mistaken with the concept of modus ponens. Premise 1. If R, then L. Premise 2. L. Conclusion. Therefore, R. First, let us do a horizontal representation of the logical structural argument. If R, then L, and L, then R. Next, we make the table of substitute instances. And then, we subsequently assign the truth values to the argument. To give an example, please examine the shaded horizontal. Notice that you have a case where the premise set is true and the conclusion is false. This makes the argument form invalid. In many arguments form where you can find a specific case where the premise set is true and the conclusion is false, the argument form is invalid. Although in an invalid argument form, it may have a specific argument that is valid. Argument form refers to all the possible combination of specific cases like the given table. An argument is valid if and only if there is no specific case where the premise set is true and the conclusion is false. Just in case the argument form has a specific argument where the premise set is true and the conclusion is false, then the argument form is invalid. Consequently, the term valid or invalid should be used to the argument form only. It is unwise to use the terms valid or invalid to a specific argument. in symbolic logic, the main emphasis is in the validity or invalidity of argument forms rather than a specific argument. The falsification method. Acuna wants to introduce you to a shortcut method of using truth table to determine whether an argument is valid or invalid. This method is clearly needed when dealing with argument forms with 3 or more statements. It is called the falsification method. You know that if a row can be found in which the premise set is true and the conclusion is false, an argument form is invalid. It capitalizes on this by seeking to refute the conclusion while proving that the premises are true. Consider the following argument: either P or Q, and either Q or R, then either P or R. Your goal is to deceive the audience by falsifying the conclusion while maintaining the truth of the premise set like this. You begin your evaluation with the conclusion. If either P or R is false, then both P and R are false as well. If both alternation, either P or Q, and either Q or R are true, then the premise set is true. To give an example, if P and R are false, the same values in the premise set should be assigned to P and R, leaving only Q. You have uncovered a row where the premise set is true and the conclusion is false, regardless of the value of Q, either truth or false. Therefore, the argument form is invalid. Let us consider the following argument. If R, then L, and if L, then C. Then, if R, then C. Remember that the first step is to falsify the conclusion while keeping the premise true. If R, then C is false. R must be true and C must be false. And if both conditionals are true, then the premise set is true. Observe that we cannot retain the truth of the premise set while maintaining the falsehood of the conclusion whatever value we assign to L. Therefore, the argument form is valid. The second conditional will be false, but the conjunction of the premise set will be false if L is true. If L is false, however, then the first conditional will be false and the conjunction of the premise set will be false. A word of caution is suitable here. You have conclusive evidence that it is an invalid argument form when you have discovered a horizontal in which the premise set is true and the conclusion is false. If you do not succeed in attempts of falsifying an argument, however, it does not mean it is valid. There are cases where other possible combinations of truth values are offered by a false conclusion. You must eliminate possible falsifying rows in a systematic way in such a case. This will be shown in the following example. You already know that the first step is to falsify the conclusion while keeping the premise set true. It is worth noting that there are 3 possible truth value combinations if the conclusion is false. To give an example, let us now apply the truth values of R and C to the first row. The next step is to assign the possible truth values for L as shown in the following. Please observe that you cannot maintain the truth of the premise set while retaining the falsity of the conclusion because the truth values in the box cannot be true. You might jump into the conclusion that it is a valid argument form since it seems that the argument could not be falsified. Please keep in mind that because it is a conjunction, there are other combinations of truth values in the conclusion. Notice that you were able to falsify the conclusion while retaining the truth of the premise set in the remaining combination of the truth values of R and C. Therefore, the argument form is invalid. Keep in mind that only one example of a horizontal where the premise set is true and the conclusion is false is enough to judge an argument form to be invalid. It does not mean that the argument is valid by not being able to succeed in doing it. The possible distribution of the truth values of a false conclusion is dictated by these possibilities. It has only one possibility if the conclusion is a single statement. There is only one possible combination of truth values to make it false if the conclusion is a disjunction or a conditional. It has three combinations, however, if the conclusion is a conjunction, and it has two combinations if the conclusion is a biconditional.